Right now, beneath a cracked shell of ice, 390 million miles from Earth, there is an ocean. Not a small one. Not a lake. An ocean containing more liquid water than every single ocean on Earth, combined. Twice over. And we've known about it for years. So why haven't you heard about this? Because the question scientists are now asking isn't just, is there water? It's something far more unsettling: what is living inside it? Wait, actually, let me back up for a second, because I jumped ahead. To understand why this ocean changes everything, we need to start somewhere most documentaries skip entirely. We need to start with the moon itself. Because before you can appreciate what's hidden inside Europa, you need to understand just how strange Europa is on the outside, and why the moment scientists first got a clear look at it, they knew something fundamental about the solar system had to be reconsidered. We're going to go into that ocean together, layer by layer. And at some point in this video, I'm going to show you a piece of data that sat unrecognized for 24 years, data collected by a spacecraft that is no longer with us, data that when scientists finally understood what they were looking at, sent shockwaves through the entire field of astrobiology. A spacecraft that flew through an ocean plume and didn't even know it. That moment is coming. First, though, let's meet the moon. Europa is the fourth of Jupiter's large moons, and it was discovered in January of 1610 by Galileo Galilei, one of 4 moons he spotted using a telescope he had essentially built himself. He named them the Medicean stars, trying to flatter his patrons. History renamed them the Galilean moons. Alongside Europa sit Io, Ganymede, and Callisto, 4 worlds orbiting the largest planet in our solar system, each remarkable in its own right. But Europa is the strange one. Europa is the one that doesn't quite fit. You know what's wild? Galileo discovered Europa in 1610 with a telescope he basically built in his garage. He had no idea what he was looking at. And honestly, neither did we, for another 369 years. Europa is slightly smaller than Earth's moon, a radius of about 1,560 kilometers. That's not remarkable. What is remarkable is its surface. When the Voyager 2 spacecraft flew through the Jovian system in 1979 and sent back the first close-up images of Europa, scientists stood in front of their monitors and went very quiet. Because they were looking at one of the smoothest surfaces in the entire solar system. Almost no craters. Almost no mountains. Just a vast, pale, cracked sphere, like a hard-boiled egg that someone had squeezed until hairline fractures ran across every inch of it. The crater problem is significant. Every solid body in the solar system gets bombarded constantly by asteroids and meteoroids. Our moon is covered in them. Mars is covered in them. Callisto, one of Jupiter's other large moons, is so heavily cratered it looks ancient and exhausted. But Europa? Almost nothing. The crater density on Europa is so low that scientists calculate its surface can be no older than 40 to 90 million years, a cosmological eye blink in a solar system that formed 4.5 billion years ago. The surface is being continuously renewed. Something is erasing the craters. Something from below is pushing up through the ice, flooding old surfaces with fresh material, and then refreezing, over and over. And then there are the lines. Europa's surface is covered in what planetary scientists call linea, long, reddish-brown streaks that run for thousands of kilometers across the ice, some of them parallel, some crossing at angles, some branching like rivers seen from altitude. They look, in photographs, like the surface of a cracked ceramic vase. Up close, these are fractures in an ice shell, and the coloration is telling a story. Spectral analysis suggests the reddish material contains salts, magnesium sulfate, sodium chloride, and potentially organic compounds that have welled up from somewhere below. The ice is not just frozen water. Something has been seeping through those cracks from a warmer interior. The mechanism driving all of this is Jupiter itself. Europa orbits Jupiter at an average distance of about 671,000 kilometers, completing one orbit every 3.5 Earth days. As it orbits, Jupiter's colossal gravitational field, and to a lesser extent the gravity of the other large moons, continuously deforms Europa. The moon is squeezed and released in a cycle, like a ball of dough being kneaded rhythmically. This is tidal flexing, and it generates an enormous amount of internal heat through friction. The heat doesn't require a nearby star. It doesn't require radioactive decay. It comes purely from the mechanical stress of orbiting something as massive as Jupiter. Europa is being heated from the inside out, constantly, by nothing more than gravity. That tidal heating, combined with the evidence from the surface, the freshness, the cracks, the chemistry of those reddish veins, pointed toward one conclusion. Something liquid existed beneath the ice. The question in 1979 was whether that was speculation or science. By 1995, it stopped being a question. The spacecraft that changed the conversation was named Galileo, in honor of the astronomer who first spotted Europa's existence 4 centuries earlier. Galileo launched in 1989 and arrived at the Jovian system in December of 1995, beginning an extended mission that would see it complete 11 dedicated flybys of Europa between 1996 and 2000. And one of the instruments on board, a magnetometer, designed to measure magnetic fields, picked up something that nobody had initially expected but that, in retrospect, seems almost inevitable. Europa has a magnetic field. Not a permanent one generated by a solid iron core, but an induced magnetic field. An induced field is created when a conductive material sits inside a fluctuating external magnetic field and generates its own opposing field in response. Jupiter generates one of the most powerful magnetic fields in the solar system, and as Europa moves through it, something inside Europa responds. The magnetometer on Galileo recorded that response precisely, and it varied in exactly the pattern you would expect if there were a layer of electrically conductive material beneath Europa's surface, rotating with the moon, responding to Jupiter's field, generating an induction signal as regular and measurable as a heartbeat. Here's the thing that makes this airtight: dry rock doesn't conduct electricity well enough. Solid ice doesn't either. To generate the magnetic induction signature that Galileo detected, you need a substantial layer of something that conducts, and the only candidate that fits, given the chemistry already known about Europa, is salt water. Liquid, salty water, probably with a conductivity similar to or higher than Earth's oceans. The magnetic data alone proved the ocean exists without anyone needing to drill a single hole. And here's the thing that gets me every time. The Galileo spacecraft was not designed to study Europa's ocean. It was designed to study Jupiter. Europa's ocean was discovered almost as a byproduct. Some of the most important discoveries in science happen that way, sideways, when you are pointing in a different direction. The gravity measurements from Galileo's flybys added a second layer of confirmation. By measuring subtle variations in Galileo's trajectory as it passed near Europa, scientists could reconstruct the moon's internal density structure. What they found was a differentiated interior, a dense iron core at the center, surrounded by a mantle of silicate rock, and then an outer layer of water and ice. The proportions suggested the water layer, ice plus liquid, extended roughly 80 to 170 kilometers from the rocky interior to the surface. And because the surface ice shell is estimated at 15 to 25 kilometers thick, that leaves somewhere between 60 and 150 kilometers of liquid ocean underneath. Then came the plumes. In 2013, the Hubble Space Telescope detected ultraviolet emission features at Europa's southern hemisphere, features consistent with water vapor venting from the surface in columns reaching approximately 200 kilometers into space. The observations were repeated in 2016. Two independent detection methods, the in situ magnetic evidence from Galileo and the remote visual evidence from Hubble, were now converging on the same story. Europa's ocean wasn't just sitting there passively beneath its ice shell. In at least some places, it was erupting outward. Water from the interior was reaching space. The debate that continued, and still continues among planetary scientists, is about the thickness of the ice shell. Two schools of thought exist. The thin ice camp argues the shell is 3 to 10 kilometers deep, allowing material to cycle relatively easily between the ocean and the surface. The thick ice camp argues for 20 to 30 kilometers. This matters enormously because ice shell thickness determines how well the ocean is connected to the surface chemistry, and surface chemistry, driven by radiation from Jupiter, is what produces the oxidants that could power life. Thin ice means a more dynamic, connected system. Thick ice means a more isolated one. Europa Clipper's ice-penetrating radar will resolve this debate within the next decade. When scientists actually ran the numbers on the volume of water implied by all of this, the volume of the ocean beneath Europa's ice, they had to check their calculations 3 times. Because the answer was almost offensive in its scale. Let me give you something to hold on to. The total volume of free liquid water in all of Earth's oceans, the Pacific, the Atlantic, the Indian, the Arctic, the Southern, every sea and connected body of salt water on this planet, is approximately 1.335 billion cubic kilometers. That number represents every shipwreck, every coral reef, every deep-sea trench, the entire volume of ocean life on Earth, every hurricane that ever drew moisture from tropical waters. All of it. Europa's ocean is estimated to contain roughly 3 times 10 to the 8th cubic kilometers of liquid water, approximately twice that entire volume. More than double. If you took every ocean on Earth, poured it into a container, and then tried to pour Europa's ocean in on top, it would overflow. Completely. Europa, a moon smaller than our own moon, contains more liquid water than the planet we live on. I want you to sit with that for a second. We have an ocean on another world, right now, as you watch this, with more water than Earth. And every time I try to fully visualize that, something in my brain kind of short-circuits. It doesn't feel proportional to the size of the object we're describing. The depth dimension makes this stranger still. Europa's ocean is thought to be between 100 and 170 kilometers deep. Compare that to the Mariana Trench, the deepest point in Earth's oceans, at just under 11 kilometers. At the bottom of Europa's ocean, where liquid water meets the rocky silicate mantle beneath, the pressure reaches thousands of atmospheres. Under those conditions, water may transition into what's called high-pressure ice, not the familiar ice of frozen lakes, but a denser crystalline form that exists only under extreme compression. Above that zone, liquid water. Above that, the underside of a 20-kilometer thick ice ceiling. No sunlight. No photosynthesis. No connection to a star. This is what scientists call a dark ocean. And the reason it matters is this: for most of human history, we assumed light was the prerequisite for life. Sunlight drives photosynthesis, photosynthesis drives the food chain supports everything else. Take away the light, and life should collapse. Europa's ocean has no light. It has never had any light. If life exists there, it is operating on a completely different energy economy, one that we did not believe was possible until we found its equivalent right here on Earth, hidden at the bottom of our own oceans. The water in Europa's ocean is not pure. Spectral analysis of the surface material suggests significant concentrations of magnesium sulfate and sodium chloride, the same compounds that dominate Earth's seawater, though possibly in different proportions. The ocean is briny. It has chemistry. It has temperature gradients, colder near the ice, potentially warmer near the rocky floor where tidal heating concentrates. And it has been liquid, according to current models, for most of the solar system's history. 4 billion years. That's not a puddle. That's a permanent environment. But size alone is not what makes scientists lose sleep over Europa. Size with the right chemical ingredients, size with a heat source, a rocky floor, and liquid water, that is the combination that turns an interesting moon into something that demands attention. Because we have seen, with our own eyes, what that combination produces. We saw it for the first time in 1977, 2 years before Voyager ever photographed Europa's cracked surface. In 1977, a submersible called Alvin, operated by the Woods Hole Oceanographic Institution, descended to the seafloor near the Galapagos Rift at a depth of about 2.5 kilometers. The researchers on board were expecting to find a cold, dark, barren environment, the kind of seafloor that constitutes most of the deep ocean. Instead, they found something that reshaped everything we knew about the conditions necessary for life. Hydrothermal vents. Seafloor chimneys venting superheated water at temperatures reaching 400 degrees Celsius, surrounded by ecosystems of remarkable density and variety. Tube worms stretching 2 meters long. Eyeless shrimp. Chemosynthetic bacteria forming thick mats across the rocks. Entire food webs, producers, consumers, decomposers, operating in total darkness, without a single photon of sunlight reaching them. The energy source was not light. It was chemistry. Specifically, reactions between hydrogen sulfide venting from the Earth's interior and dissolved oxygen in the surrounding water, a process called chemosynthesis, which allows bacteria to manufacture organic compounds using chemical energy rather than solar energy. This was a paradigm-demolishing discovery. Before 1977, the definition of a habitable environment was essentially close enough to a star that liquid water can exist on the surface. After 1977, that definition broke open. Life could exist anywhere there was liquid water and a chemical energy gradient. The location relative to a star became irrelevant. In 1977, before the Alvin expedition, if you had told a biologist that life could exist at 400 degrees Celsius in total darkness under 250 atmospheres of pressure, they would have escorted you out of the building. I think about that whenever someone says life on Europa is impossible. The connection between Earth's hydrothermal vents and Europa deepens when you look at a specific type of seafloor chemistry called serpentinization. This is a reaction that occurs when seawater contacts olivine and pyroxene, the silicate rocks that make up Europa's mantle. The reaction produces hydrogen gas as a byproduct. Hydrogen is a primary energy source for a class of microorganisms called methanogens, archaea that consume hydrogen and carbon dioxide and produce methane. Methanogens are among the oldest forms of life on Earth. They live in environments with no oxygen, no light, high pressure, and extreme temperatures. They are, in a real sense, the life form that Europa most plausibly could support. In 2000, oceanographers discovered the Lost City hydrothermal field in the Atlantic Ocean, a vent system powered not by volcanic heat but by serpentinization alone, operating at lower temperatures of roughly 40 to 90 degrees Celsius and at a highly alkaline pH between 9 and 11. Lost City is teeming with life. And its conditions, moderate temperature, alkaline water chemistry, serpentinization-driven hydrogen production, are considered the closest analog on Earth to what might exist at the bottom of Europa's ocean. This is not speculation. This is a demonstrated environment on our own planet that matches Europa's predicted conditions almost exactly. Some researchers, including William Martin at the University of Dusseldorf, have argued that the last universal common ancestor of all life on Earth, the organism or community of organisms from which every living thing on this planet descends, may itself have originated at a hydrothermal vent. If that hypothesis is correct, then the conditions in which life began on Earth are conditions that exist right now at the bottom of an ocean 390 million miles away. The implications are either deeply comforting or deeply disorienting depending on your disposition. There is one more piece of the chemistry that ties Europa's ocean to life. Jupiter's intense radiation continuously bombards Europa's icy surface, breaking apart water molecules and creating oxidants, molecular oxygen, hydrogen peroxide, and other reactive compounds. These oxidants accumulate on the surface. If cracks in geological activity allow them to be transported downward through the ice shell into the ocean, they become available as chemical reactants for life. The ocean has a reducing environment near the seafloor and potentially an oxidizing environment near the ice above. A chemical gradient. Energy available at both ends. This is exactly the kind of electrochemical setup that drives biology. We know what the conditions look like. We understand the chemistry. We have existence proofs on Earth for every individual element of the equation. The question has moved from, could there be life? To, what kind of life, and how do we look for it? And to answer that second question, we had to actually send something there. The Galileo mission was the first and, until very recently, the only spacecraft specifically designed to orbit Jupiter and study its system in detail. It launched in October of 1989 aboard the Space Shuttle Atlantis, took a complex gravitational slingshot trajectory through the inner solar system, and arrived at Jupiter in December of 1995. Over the following 7 years, it completed 11 targeted flybys of Europa, approaching as close as 200 kilometers from the surface. The data from those 11 flybys established the magnetic evidence for the ocean, refined the gravity models for Europa's interior structure, and photographed the surface at resolutions never previously achieved. Galileo was an extraordinary machine operated by an extraordinary team. And at the end of its mission, in September of 2003, NASA made a deliberate choice that I find genuinely bittersweet. They steered Galileo directly into Jupiter's atmosphere and let it burn up. The reason was planetary protection. Europa's ocean is considered a potential habitat for life. Any spacecraft that has been operating in space, picking up microorganisms from Earth's cleanroom environments, exposed to the residual biological contamination that no sterilization process fully eliminates, poses a contamination risk. If Galileo were left in an unstable orbit around Jupiter, there was a non-zero probability it would eventually impact Europa. That could not be allowed. So the spacecraft that proved the ocean existed was deliberately destroyed to protect the ocean it discovered. Like a soldier who completes the mission and then has to disappear. I find something profound about that choice. Meanwhile, in 2012 and 2016, the Hubble Space Telescope detected those ultraviolet plume signatures I mentioned earlier. And in 2021, a team led by Xianjia Jia at the University of Michigan did something remarkable. They went back to the Galileo data. Using simulation models that simply did not exist in the 1990s, they reanalyzed the magnetic and plasma wave data from a specific flyby, Europa flyby number 12, designated E12, conducted on December 16, 1997. And what they found in that old data, buried in the noise for 24 years, was a plume signature. Galileo flew through an active water plume on December 16, 1997, and no one knew it at the time. Now, in the present, we have something that Galileo did not have, Europa Clipper. Launched in October of 2024, Europa Clipper is on its way to the Jupiter system, expected to arrive in April of 2030. It carries 9 scientific instruments, including REASON, a dual-frequency ice-penetrating radar that can image the structure of Europa's ice shell down to approximately 30 kilometers, and MASSPEX, a mass spectrometer roughly 100 times more sensitive than anything Galileo carried. Its mission plan includes 49 flybys of Europa over approximately 4 years, with closest approaches of just 25 kilometers from the surface. At that altitude, if Europa is venting plumes, and the evidence strongly suggests it is, Europa Clipper will fly directly through them. MASSPEX will analyze the molecular composition of whatever it encounters. The European Space Agency's JUICE mission, launched in 2023 and focused primarily on Ganymede, will also conduct 2 Europa flybys, providing a second independent dataset. Total cost of Europa Clipper, approximately $5 billion. That sounds like a large number. When you frame it as the cost of asking whether we are alone in the solar system, it sounds like perhaps the most cost-effective scientific expenditure in human history. The challenge that lies beyond Clipper, if Clipper finds compelling evidence, is a lander. NASA has studied a Europa lander concept since 2016, but it has not received official funding approval. The technical hurdles are staggering. Any lander sent to Europa must meet Planetary Protection Category 4 requirements, meaning it must be sterilized to a degree that eliminates all traces of earthly biology. That sterilization process adds hundreds of millions of dollars to the mission cost and pushes the complexity to the limits of current engineering. But if Clipper returns data that demands follow-up, the political calculus around funding a lander will shift considerably. And beyond a lander, in the 2050s and 2060s, serious proposals exist for a cryobot, a probe that would melt through the ice shell over several years and release an autonomous submarine into the ocean below. The physics and engineering of such a mission are challenging but not contradictory to known science. So what is Europa Clipper actually looking for? What would life in Europa's ocean look like, and is there a chance we've already missed signs of it? The framework astrobiologists use begins with the 3 ingredients considered necessary for life as we understand it: liquid water, a source of chemical energy, and the relevant chemistry, specifically, the elements carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Europa almost certainly has all 3. Liquid water is established. Chemical energy via serpentinization and tidal heating is strongly predicted. The relevant elemental chemistry is consistent with spectral analysis of the surface and with models of the rocky mantle composition. The most likely biological scenario on Europa is microbial. Specifically, organisms analogous to the chemolithoautotrophs, microorganisms that derive energy from inorganic chemical reactions, consuming hydrogen and carbon dioxide to produce methane, or oxidizing sulfur compounds, or using the hydrogen peroxide delivered from the ice surface as an electron acceptor. These are not exotic life forms. Methanogens are among the oldest and most widespread life forms on Earth. They live in deep-sea sediments, in hydrothermal vent communities, in Antarctic ice, in the deepest mine shafts, essentially anywhere liquid water and chemical gradients coexist. Lake Vostok in Antarctica offers a particularly compelling comparison. Buried under nearly 4 kilometers of ice, isolated from the surface for an estimated 15 to 25 million years, the lake has never seen sunlight since long before the first hominids walked the Earth. Microbial communities have been detected in ice cores drilled from above it. Life persisted in complete darkness, under crushing pressure, through millions of years of isolation. Europa's ocean has been liquid for potentially 4 billion years. If anything, it has had more time. Multicellular life on Europa is a more speculative proposition, a minority view, but one that serious researchers do not dismiss out of hand. If the ocean has been stable for billions of years, if hydrothermal systems have maintained consistent energy gradients throughout that time, there is no physical law prohibiting the emergence of more complex organisms. We simply do not know. The honest position is, we don't know. One potential constraint is phosphorus. The element is essential for DNA and for adenosine triphosphate, the molecule that drives cellular energy transfer. Some researchers, examining the likely rock chemistry of Europa's mantle, have raised questions about phosphorus availability. If Europa's silicate mantle is phosphorus poor, that could represent a genuine bottleneck for complex life. However, serpentinization reactions, the same ones that produce hydrogen, also have the capacity to release phosphorus from rock matrices into the water column. The question is unresolved, and it is one that analyses of plume composition by Europa Clipper could potentially address. Here's something I think people miss in this conversation. We keep framing the life question as a binary, yes or no, life or no life, as if those are the only outcomes that matter. But even the most conservative positive result, even, there are methanogens in a vent community at the bottom of Europa's ocean, would be the most consequential discovery in the history of human civilization. No asterisk. No qualification. The confirmation that life arose independently on two worlds within the same solar system would statistically imply that life is not a fluke. That it arises wherever conditions permit. That the universe is full of it. And that brings us to the evidence that created 3 years of uncomfortable silence. The data from December 16, 1997, that nobody recognized for what it was until 2021. Let me walk you through what Galileo experienced on that day. The flyby designated E12 brought the spacecraft to within 206 kilometers of Europa's surface, close enough that its instruments were sampling the immediate environment around the Moon. The magnetometer and the plasma wave spectrometer both recorded anomalies during a window lasting approximately half a minute. These anomalies looked, at the time, like minor electromagnetic disturbances, the kind of thing that ends up in a data footnote, noted and set aside. In 2018, Shinja Jia and his team at the University of Michigan published a paper in Nature Astronomy presenting new simulation models of what a Europa water plume would look like to a spacecraft flying through it. They described the expected magnetic field perturbations, the predicted plasma density spikes, the characteristic signature of ionized water vapor interacting with Jupiter's magnetic environment. And when they ran those models against the E12 anomaly data, the pattern matched. Precisely. The magnetic field perturbations recorded during those 30 seconds of Galileo's flyby were consistent with flying through a column of conducting, ionized seawater rising from Europa's surface. Galileo flew through an ocean plume. It collected material from inside that plume. The data is sitting in archives, 24 years old, and it contains information about the chemistry of Europa's ocean, chemistry that Galileo's instruments were not sensitive enough to fully resolve, but chemistry that was recorded nonetheless. The plasma wave instrument logged a density spike during those same 30 seconds, an increase in the concentration of charged particles consistent with the ionization of water vapor in a plume column. Duration, half a minute. Signature, exactly what plume models predict. False positive probability, assessed as extremely low by independent reviewers of the Jia et al. Paper. I've read that paper 3 times. And every time I reached the section where they describe Galileo flying through the plume, a machine built in the 1980s by engineers who are now retired or no longer with us, and it caught something this significant without anyone knowing, the sensation is difficult to describe. Not quite chills. More like the feeling of a very large door swinging open on silent hinges. The Hubble visual confirmation ties directly to this. In 2013 and 2016, Hubble detected ultraviolet emission features above Europa's southern hemisphere, tentatively identified as water vapor rising in columns to approximately 200 kilometers altitude. The Hubble evidence and the Galileo in situ evidence are independent. They were collected by different instruments, at different times, using completely different detection methods. They point to the same conclusion: Europa is actively venting material from its interior into space. The ocean is not sealed. It is breathing. The plume output rate is estimated at roughly 7,000 kilograms of water per second during active periods, an enormous volume of ocean material dispersing into the vacuum around Europa continuously. When Europa Clipper arrives and conducts its closest flybys, its MASSPEX instrument, with its 100-fold improvement in sensitivity over Galileo's instruments, will be able to analyze the molecular composition of that material directly. It can detect amino acids. It can detect lipid-like compounds. It can identify nucleobases. It can measure isotope ratios. It can look for the kind of chemical complexity that, on Earth, is associated exclusively with biology. This is the test. The actual test. The one with real instruments, targeted specifically at this question. It is arriving in 2030. Europa is not alone in its implications. The discovery of its subsurface ocean has transformed the way scientists think about habitability across the solar system and beyond. For most of the 20th century, the habitable zone concept was straightforward: a star emits energy, a planet must orbit at a distance where that energy allows liquid water on the surface, and that narrow band of orbital distances is called the habitable zone. Earth sits inside the Sun's habitable zone. Mars is at the edge. Venus is inside it but lost its water to a runaway greenhouse effect. The model made sense. Europa demolished it. Europa is 5.2 astronomical units from the Sun, well beyond where solar energy can maintain liquid surface water on any reasonable world. Europa's ocean exists because of tidal heating, which requires no star at all. The energy source is purely gravitational, driven by the mass of Jupiter and the orbital resonances between its moons. This means that the habitable zone concept, as a framework for identifying candidate worlds for life, has been too conservative by orders of magnitude. Enceladus, orbiting Saturn, validates this directly. In 2017, NASA's Cassini spacecraft flew through Enceladus's plumes and detected molecular hydrogen, carbon dioxide, and complex organic molecules, the signature of active hydrothermal chemistry on Enceladus's seafloor. Cassini tasted that moon's ocean and found it had the ingredients for chemosynthetic life. Enceladus is smaller than Europa, a radius of just 252 kilometers, and it has a subsurface ocean. If Enceladus can, Europa certainly can. Ganymede, Callisto, and Titan, all within our own solar system, are suspected to have subsurface liquid layers of various kinds. Titan has lakes of liquid methane on its surface, raising the possibility of a completely different solvent-based biochemistry. The solar system we thought we understood, a handful of rocky inner planets with one habitable surface and everything else cold and dead, turns out to be riddled with liquid environments. The galactic extrapolation from this is staggering. If tidal heating is a viable energy source for habitable environments, then every gas giant planet with icy moons becomes a candidate. In the Milky Way alone, there are estimated to be hundreds of billions of gas giant planets. Many of them likely host multiple icy moons. The number of potentially habitable environments in the galaxy stops being counted in dozens and starts being counted in the hundreds of billions. I'll be honest, when I started researching this video, I thought I'd find one or two interesting facts about Europa. Instead, I spent 3 weeks climbing out of a rabbit hole that kept getting deeper. Somewhere along the way, I realized this is not a story about a moon. It's a story about what life actually is, and how narrowly we had been defining the places worth looking. There's a dimension of this that connects to the Fermi paradox, the old question of why, if intelligent life is common in the galaxy, we have seen no evidence of it. Part of the answer may be that most life in the universe is not on the surface of planets where it can build radio telescopes and broadcast signals into space. Most life may be deep inside dark oceans under ice, living at hydrothermal vents, running entirely on chemical energy, never interacting with the electromagnetic spectrum in any detectable way. The universe could be teeming with biology that is permanently silent, not because it is rare, but because it has no reason to announce itself to the stars above an ice ceiling it has never seen. Europa Clipper will reach the Jupiter system in April of 2030. Over the following 4 years, it will complete those 49 flybys of Europa, sun distant, some at 25 kilometers, some specifically targeted at locations where plume activity has been detected. The first scientific results should begin arriving in 2031. Data relevant to the life question, if the instruments detect what they are capable of detecting, could be in hand by 2032 or 2033. The mission has a tiered structure of discovery goals. The first tier, confirming the ocean's depth, salinity, and ice shell thickness, is almost certain to be achieved. The instruments exist, the measurements are straightforward in principle. The second tier, detecting organic molecules in plume material, is possible, contingent on encountering active plumes during flybys. The third tier, detecting biosignatures, meaning chemical patterns that can only be plausibly explained by biological processes, is the dream. It is not listed in the official mission goals. But the instruments can, in principle, do it. If Clipper finds compelling evidence, the conversation about a Europa lander will change dramatically. A surface mission, one that could deploy sensors directly onto the ice, potentially drill into the ice shell, sample freshly deposited plume material that has refrozen on the surface, would represent the next step. The planetary protection requirements for such a mission are extraordinary. Everything would need to be sterilized to a degree that eliminates all known biological contamination. The cost adds hundreds of millions. But the science justifies it. The engineers and scientists who built and launched Europa Clipper know what they might be carrying toward the outer solar system. There is a chance, a real, non-negligible chance, that the machine they built, the machine that is traveling through space right now as you watch this video, will return data that tells humanity it is not alone in its own solar system. They are the people who built that instrument. I cannot think of a more extraordinary thing to have worked on. The longer arc, drilling through the ice, deploying a submarine into Europa's ocean, belongs to the 2050s or 2060s at the earliest. JPL and DARPA have both run studies on cryobot concepts, probes that use thermal energy to melt through kilometers of ice over years, then release an autonomous hydrobot to navigate the dark water below. The physics are demanding. The engineering is at the frontier of what is currently feasible. But nothing about these proposals violates known science. The only obstacles are time, money, and the political will to ask the question seriously. Let me bring this home, because I think the numbers and the instruments and the mission timelines can sometimes obscure what is actually being said here. If life exists in Europa's ocean, even microbial life, even a single chemosynthetic archaeon clinging to a hydrothermal vent at the bottom of a dark sea, the consequences extend far beyond planetary science. They reach into every framework humans have built for understanding our place in the universe. Physicist Lee Cronin and colleagues working on assembly theory have proposed that life is not a singular miracle but a physical process, that any sufficiently complex chemical system, given enough time and the right energy gradients, will drift towards self-replicating, information-rich structures. Not as a lucky accident, but as an attractor state of matter. If this is correct, Europa is not just a place that might have life. It is a test of whether chemistry itself tends toward life whenever conditions allow. The history of science includes a handful of moments where humanity had to fundamentally revise its understanding of its own position. The Copernican realization that Earth is not the center of the cosmos. The Darwinian understanding that humans are not separately created but are continuous with all other life. Each of those revisions was painful and gradual and ultimately liberating. The confirmation of life in Europa's ocean would be a third revision of that scale, the demonstration that life on Earth is not a unique accident but a local example of something the universe does regularly. This also raises a question that humanity is not yet prepared to answer. If there is life in Europa's ocean, what are our obligations to it? Planetary protection shifts from a technical precaution to a moral responsibility. An ecosystem that evolved independently over 4 billion years, adapted to conditions that bear almost no resemblance to anything on Earth's surface, would be irreplaceable. The contamination of that ecosystem, with earthly microorganisms capable of outcompeting native life, or simply disrupting chemistry that took billions of years to establish, would be a loss of staggering magnitude. We have not had a serious public conversation about this. We probably need to. The psychological dimension is quieter but no less significant. One of the deep drivers of human interest in space science is what I would call the fear of cosmic loneliness, the unsettling possibility that in a universe of hundreds of billions of galaxies, each containing hundreds of billions of stars, the only life anywhere is the life on this single, particular planet. If Europa has life, that fear is answered. Not by intelligent neighbors, not by radio signals from distant civilizations, but by the simple fact of a microbe in the dark water of a moon in our own backyard. We are not alone. The company is quiet and very small and lives under 20 kilometers of ice, but it is company. I started this video with a fact: an ocean twice the size of Earth's, hidden beneath cracked ice on a moon of Jupiter. But what I actually wanted to say, what 3 weeks of research kept pointing toward, is this. We are living in the decade that may answer the oldest question. The people who will hear that answer are alive right now. Some of them are watching this video. Remember the question I asked at the beginning: why haven't you heard about this? I think the honest answer is that we don't yet have language adequate to the significance of what is being described. An ocean twice the size of Earth, plumes of water venting into space, hydrothermal chemistry almost identical to the conditions where life began on our own planet, a spacecraft already in transit that carries instruments sensitive enough to taste biosignatures in a plume fly-through. We are standing at the edge of something enormous, and the vocabulary we have, interesting, significant, potentially habitable, keeps failing to carry the weight. The universe, it turns out, may not be a sterile expanse waiting for Earth to be the special case. It may be full of dark oceans under ice, heated by gravity, running on chemistry, harboring life that has never seen a star. That does not make us less remarkable. If anything, it makes our curiosity, the drive that built Galileo in 1989 and Europa Clipper in 2024 and pointed them toward a cracked moon 390 million miles away, it makes that curiosity the most remarkable thing of all. In this space documentary, we dove into Europa, Jupiter's icy moon, and what we found reshaping everything we thought about the conditions life requires. An ocean holding more water than all of Earth's seas combined. Plumes venting that water into space. Hydrothermal chemistry at the seafloor that mirrors the environments where life on our own planet may have first taken hold. A spacecraft launched in 2024 already traveling toward a 2030 arrival, carrying instruments capable of doing something no probe has ever done, directly sampling and chemically analyzing material from inside an alien ocean. All of this is real. All of this is documented. And the answer, the actual answer to whether something is alive in that dark water right now, is coming within the lifetimes of most of the people watching this. Next time, we're going even further. Because Europa isn't alone. There is another moon in our solar system, smaller, quieter, orbiting a different gas giant, that some scientists now argue has an even stronger case for active, detectable life. One that a spacecraft already tasted. And what it found in that taste requires an entire video to unpack properly. That one is coming very soon, and if Europa's ocean kept you here for an hour, what Enceladus has to say will make this look like an introduction. But before we get to Enceladus, and we will, I promise that video is coming, there is one more piece of the Europa picture that most documentaries skip entirely. And it is, in my opinion, the piece that makes everything else make sense. We have spent this entire video talking about Europa as if it exists in isolation. A moon. An ocean. A possible biosphere. But Europa does not exist in isolation. It exists inside a solar system that, over the last 20 years, has revealed itself to be staggeringly more wet, more chemically active, and more potentially habitable than anyone expected when Voyager first photographed the outer planets in the 1970s. Understanding where Europa fits in that larger picture, understanding what the existence of this ocean tells us about the frequency of habitable worlds across the cosmos, is the difference between thinking of Europa as a curiosity and thinking of it as a data point that reshapes the entire equation. So let's step into that bigger picture. Because once you see it, you cannot unsee it. When astronomers talk about the habitable zone, the so-called Goldilocks region around a star where liquid water can exist on a planetary surface, they are describing a condition based entirely on sunlight. The logic is simple: too close to the star, water boils away; too far from the star, water freezes solid. Earth sits comfortably in the middle. Mars is on the outer edge. Venus overshot the inner boundary. For most of the 20th century, this framework defined the entire conversation about where life could exist in the universe. Europa breaks that framework completely. Europa receives roughly 25 times less solar energy than Earth does. By every traditional calculation, it should be a frozen, dead rock. Instead, it contains more liquid water than Earth. The energy source is not the sun, it is gravity. Jupiter's tidal forces flex Europa's interior constantly, generating enough heat to maintain a global ocean beneath the ice. This is called tidal heating, and it means that the habitable zone around a star is not the only place in the cosmos where liquid water can exist. Any moon orbiting a sufficiently massive planet, anywhere, at any distance from any star, is a candidate. Think about what that does to the numbers. There are roughly 200 billion stars in the Milky Way alone. Around many of them, astronomers now know, there are gas giants. Around those gas giants, there are moons. The Galilean moons of Jupiter are 4 out of what is estimated to be potentially dozens or hundreds of moons in the outer solar system, and our solar system is not unusual. If tidal heating can produce a habitable ocean at Europa's distance from the Sun, 5 times Earth's distance, far outside any conventional habitable zone, then the number of potentially habitable environments in the galaxy is not measured in the hundreds or thousands of Earth-like planets orbiting Sun-like stars in narrow Goldilocks bands. It is measured in the millions. Possibly the hundreds of millions. Every gas giant with a warm, flexed moon is a candidate. And the universe, it turns out, is full of gas giants. This is the quiet revolution happening in astrobiology right now. The habitable zone is not a ring. It is a volume. It extends, thanks to tidal forces, gravity, radioactive decay, and subsurface chemistry, to almost anywhere a rocky or icy body has sufficient internal energy to keep water liquid. Europa proved this was possible in our own solar system. The implication, and researchers are explicit about this, is that life, if it arises wherever liquid water and chemical gradients exist, is not a rare accident concentrated in a thin belt around each star. It is a phenomenon potentially distributed throughout galaxies at a density no one was prepared for before Europa showed its hand. I want to be careful here not to overstate. The existence of liquid water does not guarantee life. We have liquid water in hydrothermal vent systems on Earth's ocean floors, and not every vent hosts thriving ecosystems, though many do. The conditions need to be right, the right chemistry, the right energy flux, the right mineral interactions. Europa's ocean has all of these in principle, but principle is not the same as confirmation. What the bigger picture does is shift the prior probability. Before Europa, the reasonable assumption was that life required surface conditions, sunlight, and a specific orbital distance from a star. After Europa, that assumption looks like a parochial bias born from having only one example. The prior probability of life being widespread just increased by a factor that is difficult to calculate but impossible to ignore. And Europa is not the only moon making this argument. Saturn's moon Enceladus, which I mentioned at the close of the last section, vents plumes of water ice from an internal ocean confirmed to contain organic molecules, hydrogen gas produced by hydrothermal reactions, and silica nanoparticles indicating active rock-water interactions at temperature above 90 degrees Celsius. The Cassini spacecraft, during its final orbital phase, flew directly through those plumes and tasted them. What it found was chemistry so close to the conditions inside Earth's hydrothermal vent systems that the team lead, Hunter Wade of the Southwest Research Institute, said directly that Enceladus has the ingredients for life as we know it. Saturn's moon Titan has lakes of liquid methane and a dense nitrogen atmosphere. The chemistry is utterly different from Earth's water-based biology, but it opens the question of whether life based on different solvents is theoretically possible. Jupiter's moon Ganymede, the largest moon in the solar system, has a subsurface ocean confirmed by Hubble in 2015. Callisto, Jupiter's outermost Galilean moon, likely has one too. In our solar system, one star, one moderate planetary system, we have identified at minimum 4, and possibly 6, moons that harbor or potentially harbor subsurface liquid water oceans. 4 to 6 candidate environments in a single solar system. Scale that across the Milky Way and you arrive at a number that makes the phrase, "we might not be alone," sound like a severe understatement. There is one more thing I want to say about Europa specifically, and it is something I have been circling around for this entire video without quite saying outright. The reason Europa matters, the reason this ocean, twice the size of Earth's, hidden under ice, heated by gravity, running on chemistry that mirrors our own deep-sea vents, actually matters, is not the ocean itself. It is the timing. We are the first generation of humans who can do something about this question. Galileo discovered Europa in 1610, but for nearly 4 centuries, all we could do was look at it from Earth and wonder. Voyager gave us photographs in the 1970s. Galileo gave us close-up data in the 1990s. And now Europa Clipper, launched in October 2024, currently in transit, scheduled to arrive in 2030, will give us something no human instrument has ever delivered: direct chemical analysis of material sourced from inside an alien ocean. For every previous generation of humans who ever looked up at the night sky and asked whether anything else was out there, this moment, this decade, is the answer to that question arriving. Not as philosophy. Not as speculation. As data. As instrument readings. As molecular analysis from a spacecraft that costs $5 billion and carries 10 science instruments and was built by humans who spent decades of their careers asking the same question you are asking right now: are we alone? If that is not worth an hour of your attention, I genuinely do not know what is. And if the answer turns out to be yes, yes, something is alive in that dark water, yes, the universe makes life wherever the conditions allow, then the hour you spent here will be the hour before everything changed. So keep watching the sky. Keep following the science. And when Europa Clipper makes its first plume fly-through and the data starts coming back, remember that you already know what to look for, because you were here when we mapped the whole thing out, one frozen crack at a time. And that, right there, is the thing that keeps me coming back to this subject every time I sit down to research a new video. Not the raw numbers, though the numbers are staggering. Not the engineering, though the engineering is genuinely one of the most ambitious things our species has ever attempted. It is the timing. The sheer, improbable, almost unfair timing of being alive right now, when the instruments are finally good enough, the spacecraft finally fast enough, the science finally precise enough to go get the answer. We started this journey with a cracked shell of ice orbiting a gas giant 390 million miles away. We traced the magnetic fingerprints that revealed a global ocean no telescope could directly see. We mapped that ocean, 100 kilometers deep, more liquid water than every sea on Earth combined, twice over, and asked how it stays warm, and found the answer in tidal flexing, in the relentless gravitational squeeze of Jupiter's massive hand. We went down to the seafloor and found, in the hydrothermal systems of Earth's own deep ocean, a working blueprint for how chemistry becomes biology in the absence of sunlight. We followed the plumes, those extraordinary vapor fountains punching through 30 kilometers of ice, and held the data in our hands: water vapor, salt, carbon dioxide, hydrogen peroxide, and the organic signal that made an entire scientific community go very, very quiet for a moment before the questions started pouring out. We are not speculating about whether Europa's ocean exists. That argument is settled. The ocean is real, it is enormous, it has been liquid for potentially billions of years, and it is sitting there right now, dark and pressurized and chemically active, doing whatever it does, with or without our observation, with or without our curiosity, completely indifferent to whether we ever figure it out. The question that remains is the only question that has ever really mattered in the history of human astronomy: is anything in there with it? I should be honest about one thing before we close. I came into this subject assuming I would feel more certain by the end. I thought the more I read, the more the answer would sharpen into focus, either a confident yes, pointing at the chemistry and the analogs and the billions of years of stability, or a cautious no, reminding myself that one data point is not a pattern and that Earth life is the only life we have confirmed in 13.8 billion years of cosmic history. What I actually found was something more uncomfortable and, I think, more honest. The evidence keeps making the case stronger without ever crossing the line into proof. Every new dataset moves the needle. None of them moves it all the way. And that unresolved tension, that open loop in the data, is exactly where good science lives. The researchers working on this are not dreamers pretending certainty they do not have. Brittany Schmidt, Kevin Hand, Cynthia Phillips, Hunter Waite, the entire teams at JPL and the SETI Institute, these are people who are scrupulously careful about the difference between conditions consistent with life and evidence of life. They will tell you, if you ask, that we do not know yet. But they will also tell you, and this matters, that we have never been this close to being able to find out. Europa Clipper arrives in 2030. Its instruments will sample plume material if active venting is occurring during its flybys. It will map the ice shell thickness. It will profile the magnetic environment at precision levels that should finally distinguish between different models of the ocean's chemistry. It will not land. It will not drill. It will not dip a sensor into the water directly. But it will deliver a portrait of Europa so detailed that the next mission, the lander, the one that comes after, will know exactly where to put down, exactly where the cracks are youngest, exactly which plumes to sample at the surface where ocean material has freshly arrived. The decade from 2030 to 2040 will be, in the history of astrobiology, the decade we remember. Either as the decade we confirm that life exists beyond Earth, or as the decade we learn precisely enough about Europa to design the instrument that will confirm it in the decade after. Either outcome moves our understanding of the universe in a direction that cannot be undone. There is a photograph I keep coming back to. It was taken by the Galileo spacecraft in the late 1990s, a close-up of Europa's surface showing a region called Connemara chaos, where the ice shell appears to have broken into large plates and then refrozen in shifted positions, like a jigsaw puzzle someone dropped and pressed back together slightly raw. The cracks between the plates are stained red and brown by the same salt compounds and organic materials that the ocean carries up from below. Under the low-angle light of a distant sun, the surface looks less like a moon and more like something that has been through a process, something that has been active, changing, cycling material between interior and surface for a very long time. When I look at that image, I do not see rock and ice. I see a door. A sealed, frozen, 30-kilometer thick door, and behind it, an ocean that has been waiting in the dark for longer than multicellular life has existed on Earth. The question of whether we knock on that door, and what answers when we do, is the defining scientific question of the next 20 years. You know what is in there now. You know how we found it, why we believe it, what the evidence says, and what comes next. So when the news breaks, when Europa Clipper sends its first confirmed plume fly-through data back across 390 million miles of space and every science journalist on Earth writes their headline, you will not be reading that story for the first time. You will be reading the confirmation of something you already understood, because you were paying attention before it was the biggest story in human history. And honestly, that ocean has been down there for 4 billion years without any acknowledgement from us at all. The least we can do is show up on time. If that does not make you want to be alive for the next 20 years, I genuinely do not know what else this universe has left to offer you, but I suspect Europa is working on something. The hook section and the closing CTA are the two pieces left to place, and the outro is already sitting right there in the final paragraphs, so what remains is the opening, the 30 seconds that either pull someone in or send them scrolling to the next video forever. Wait, actually, let me back up for a second, because I jumped ahead there. To understand why this ocean changes everything we thought we knew about life in the universe, we need to start somewhere most documentaries skip entirely. We need to start with the moon itself, a small, smooth, cracked ball of ice orbiting a gas giant so enormous it could swallow 1,000 Earths, and ask the question that nobody asked loudly enough for the first 3 centuries after we discovered it: why does this thing even exist the way it does? Because here is the truth behind Europa that reshapes everything. We are going to journey into that ocean together, layer by layer, discovery by discovery, and at the end of this, you will walk away with something that very few people outside a small community of planetary scientists actually carry around with them: the genuine understanding of why Europa is not a curiosity at the edge of the solar system, but the most important object in the history of the search for life beyond Earth. That is not hype. That is where the evidence leads. And we are about to follow it all the way down. And if you want to be in that room when the answer finally arrives, subscribe, because when Europa Clipper phones home, we are going to cover every single transmission together. The decade from 2030 to 2040 belongs to everyone who was curious enough to look up before the headlines told them to, and you are already here, which means you are already ahead of the story. If 4 billion years of waiting in the dark does not count as patience, then nothing in this universe does, and when Europa finally gets its answer, remember that you were asking the question long before the rest of the world caught up.